Hello, hi. Good evening, everybody. Let's wait for a few minutes so that others can also join, and we will start by by 7:375 something. Let others also join.
Okay, madam.
Hello, we'll start at around 7. Okay, hi. Hello, hi. So we'll start at around 7:475-ish. We'll just give some more time for others to join, and then we'll begin. Hello, Hall. Hi, good evening to today's session. I'm just sharing my presentation and we will begin now. I'm audible, right? Yeah, I think Hello. Hi, and welcome to today's tutorial session. So, most of you were there in the previous session, so I need not give much of an introduction. But so I think all of you were there in the previous one. So I'll just directly go on to the questions and we'll directly start discussing. So, week three. So this today's discussion will be on week three topics, whatever we discussed. So we had 5 lectures in this. We learned about rainfall, what is runoff, surface runoff, subsurface runoff, what is groundwater, how do we measure it, and what are the different properties, flow characteristics, what are how groundwater intakes and its issues. We'll also learn some numericals on how do we calculate groundwater yield, specific yield, some theorems like Thiem's theorem, all those we learned. Plus, we also looked into how do we take surface water intakes, like how do we take the surface water using certain uh, pumps and etc. So the problems or the questions, assignment questions, which we will be discussing today will be based on these topics. Towards the end, if you had any doubts regarding previous assignments, we can discuss that also. So, yes. Yeah, so this you're already familiar with, but just to I'm just mentioning it once more. So today I have around 7 or 8 questions. So we'll discuss one by one, and whatever doubts you have, you can ask immediately after that question. And by the end, also we'll have like a 5 to 10 minute discussion. So today, thankfully, everything is working properly. So we'll be solving it together. So I highly suggest that all of you have a scientific calculator with you, because this would you can do the calculations much easier in that. We have certain log and those calculations coming in today's discussion. So if that's there, grab it, and obviously a pen and a paper, because we'll be solving it together. So I'll be asking you for the answers. So yeah, so if you can take some time to grab it, or we'll proceed further. So if you're all set, we can proceed further. If I can just have a quick confirmation, all set, can I proceed? You can put in the chat box, or you can.
Yes, ma'am.
Okay,
Yes, madam,
great.
we are all ready. Please.
Great, great. So let's directly dive on to our first question. So our first question, I'll just read it out. A real estate project on a 15-hectare site contains 8 high-rise apartments, each with ground coverage of 2% of the site area, and houses a residential population of 18,000. 40% of the site area is for landscaped gardens and parks. The rest of the area is for roads and open parking. The site experiences rainfall of 1,580 millimeter annually. Assume the coefficient of runoff for landscape area and paved areas to be 0.15 and 0.65 respectively. The average surface runoff from the site after a heavy rainfall of 150 millimeter in 2 hours is. So basically, we have been asked to find what is the surface runoff. So just to revisit on what do we mean by surface runoff. So whenever rain falls on the surface, there's obviously like there's rainwater. Some percolates down, like infiltrates down. So then we have a subsurface runoff happening over here. So here the question specifically asks what is the surface runoff? That is from the surface, how much of water is flowing on to the river. So by definition, that is what surface runoff also means. Like how much of water is coming on to the river or the nearby water body which is there, or surface water body which is there. So this particular question is asking us to find, yeah. So this particular question is asking us to find what is the surface runoff, and we have a lot of information given in the question. It might be a bit intimidating, but maybe we don't need all the information. We can just pick out the information that we require. So let's just start by writing whatever information we have. So first one, we've been given the site area. So we have the site area to be 15 hectares, right? Then the second one, we have been given that there are 8 high-rise apartments with each having a ground coverage of 2%, which means if this is our site and we have got 8 buildings, so I'm just drawing it very roughly. We've got 8 buildings. So each, if they cover around 2%, and the ground coverage of 2% each, which means the total roof area that these will be covering, like let's just take the roof area, that is where the rain will be falling on the roof, that will be 8 into 2 by 100, that is 2% of the site area, which is 15 hectares. So I hope all of us are here. So this calculates to a very quick calculation, 8 into 2, 16 into 15. So divided by, so how much does this come up to? Quick. Anybody? Nobody? Okay, that's surprising. Yeah, I'll just keep the chat box open. So Okay, I'm just going to leave it there if nobody is going to respond. It's a very easy calculation. So, and we've also been given the total population, that is 18,000. If you get the answer for this, that is what is the roof area in hectares, please put it in the chat box. It's just 8 into 2 into 15 by 100. Yeah. So coming back, we have a population. So our total population is 18,000. That is also given. And now we've got 40% of the area for landscape gardens. So that information also we need. So how much do we have for landscape? So we have 40 by 100 into 15 hectares. This is, okay, I think I'll just go ahead and write these. And for roads, the next one is for roads. So we have roads and open parking. So that is given the rest of the area. So how do we calculate the rest of the area? So we obviously need this over here. So this calculation comes up to 2.4 hectares. And so the rest of the area will be now, our total is 15 hectares. 15 hectares minus, we'll add this up, 2.4 plus 6. Everybody with me till here? So this is the amount of area that we have for roads and parking. Sorry, roads or parking together. So now we have all the areas that we have. So basically this much of information is given to us. We also know what is the annual rainfall and the coefficient of runoff. For that both it's given. So now I'm just going on to the next page. So what we've been asked is to find the surface runoff. So in the lectures, we have already discussed about how do we find surface runoff. A formula was also given. So it's given that surface runoff Q is equal to CIA by 360 and the unit comes in meter cube per second. Like this will be the surface runoff which is there. So here I'm just explaining. So the C is our coefficient of runoff or the runoff coefficient for each surface which is there, coefficient of runoff. So this is already given in our question, so we already have that. Now what is I? I is basically the intensity of rainfall. Intensity of rainfall. And this one consideration that we have to make is that I is measured in hours. It's so like the unit that you put in here should be in hours, that how in intensity of rainfall in hours. And A is the area in hectares. So we have already got the site area or the area which we are considering in hectares. So this is already given in hectares, so it's not an issue. But if you look our annual rainfall from our question, let's just go back to the question. Our annual rainfall is given as 180 mm. Sorry, 1580 mm. So we'll have to convert this. That would be our yeah. So our annual, yeah. Okay, let's just come back to this one. Maybe we don't need that. Like let's just go by the formula. So let's go with the surface runoff for landscape area. For the first one, I'm just going with the landscape area, QL, landscape area. I'm just plugging in the formula. So let me just go back for landscape area. It's 0.15, which is given. For landscape area, the coefficient is given to be 0.15. So I'm just putting it here, 0.15 into the intensity of, hello, yeah. Hello, am I audible? Hello? Yeah, okay.
Yes, ma'am.
Yeah, sorry, I couldn't hear myself. Yeah, cool. So intensity of rainfall, as I said, we were given it as, okay, I missed out one information here. The last part which is there, which is after a heavy rainfall of 150 millimeters in 2 hours. So this is what we need to take, and we need to find in 1 hour how much rainfall is happening. Like it's given in 2 hours. So this is for the annual. We don't need this information. So that's why I said some information which is given, we don't need it. So the information we need to take from here is this 150, which is there in 2 hours. So obviously in 1 hour, we will have 75 mm. So that is the information which we will be taking over here. So 75 into, so and obviously the area. So how much area? So for landscape, we already found what is the area which was there. So I'm just going back. So it is the 6 sectors which we already found here. So 6. Now divided by 360. Now this is a very easy calculation. Can somebody just quickly do this and let me know what is the final answer? Very good, Asmita. Very good. Yeah, it is 0.1875, which we will just approximate it to 0.19 because we also need to look into our options also. So, okay, yeah. So, I mean, we are not yet done. We only did for the landscape area. So now we also need to find for roads. So let's just find. So that is QR I'm writing. Again, the same thing I'm applying. So here the coefficient is 0.65, which is given in the question, into again 75 into the area, which we already found it as 6.6 divided by 360. Okay, can you do this calculation quickly? Devasena, Tamanna, yeah, if somebody can give. Okay, ML 0.893. Yeah, right. It is correct. It is for, yeah, 0.9 approximately. Yeah, sorry. That's it. Yeah. Sorry, I'll come back to this question. My slide just moved a bit ahead. Uh, 1 minute. Yeah, sorry. Yeah, so it's the correct answer. So it's 0.89. So we can approximate it to be 0.9. So now let's add this up because we want to find the total runoff. Total runoff will be equal to 0.19 plus zero point 0.9. So can you give me the answer? Right. So which suits our option? So we have 1.08 and we got 1.09. So this is the best answer that we can get. So option A is our answer for this question. Now, if you notice, we only took the runoff from the roof area as well as the landscape area. Sorry, not roof area. We only took it from the landscape area and the road area. We did not take it from the roof area. Can somebody reason out why we did not take it from the roof area?
Basically, the rainwater which is collected from the roof, it goes as groundwater recharge through pipes.
Very
It
good.
does not act as a surface runoff.
Very good. Exactly. That's the answer. So whatever is connected from the roof does not act as a surface runoff. So this is a very important point because usually this is where the calculations go wrong because we might assume that whatever is there in the terrace or the roof, we capture that and that is also put down. No, but it's usually drained through pipes. So that is good. So I think this question is clear right now. Any doubts in this question before we move on to the next question? I'll just hold for 1 or 2 minutes. I think no doubt. So let's proceed on to the next question. Because these questions might be or in the lectures already it's been discussed, so it should be fine. Last we'll do some questions which are not discussed in the lectures also. So this question we are basically talking about. So let's just look at this. I'll just read the question. Consider the following diagram and the observations made on a 30-meter diameter tube well. So we have some information like what is rate of pumping, drawdown in a test well, draw. So what is this basically? Like what does this image show? So it's basically showing, it talks about that we know that we have a water table. And if this is the water table, which is like you have the ground and like you have the ground and you have, and okay, so imagine this is a water table. Now sorry, back to the slide. Yeah. So once we dig a well and once we start drawing water from this particular, from a well or any source that takes water out, water will start rushing in, like we are taking water in from them. So now this creates a depression. So this depression is also known as the cone of depression. And now why a cone? Because it's, if you look at like if this is the section which I've shown. So if you have a plan, then like if you have a well over here, it actually affects the entire radius, that is all the regions around it. That is, if I'm taking a view, it basically affects like this. That is, the water table, which was normally like this, would now bend like this, and it actually happens in a conical fashion. So that's why this bend, or this is known as a cone of depression. Now that is what is shown in this figure over here. So this, what we have is the main well, and water is being drawn out from this well, and due to this, there is a cone of depression which has happened. That is, the water table is bending over here. And now, how does this influence? Now, because of this bend, if I have another well over here, it means we would expect the water to be here. Like, we would expect to get water from here, but we would actually get it from here only. So if we are digging a well over here, then we'll have to dig further. So this influences. So there is a radius of influence which is happening because of this cone of depression. There is a radius around which the well is located. Some influence is happening. So this figure, or this question, basically talks about how do we design wells, or how do we place wells, and what is the region of this influence, or how do we calculate this. And this is from a test where we dig certain test wells. These are certain test wells, and based on the water level in these test wells, we will be able to predict, because if you look, it's a proper cone, or there's a proper diagram. So we will be able to predict what is the region which is influencing. So the next three questions will be related to this particular figure, that is how it is being influenced. So we have some information here which we will take as and when the question comes. So the first question is, what is the radius of the circle of influence, or R? So as I was discussing, our radius of influence basically talks about this whole radius, that is from which point the water table is starting to bend. So this is the whole radius. So that is denoted by capital R, and that is what we've been asked to find. We also have certain these other distances where we have dug the tube well, which might be somewhere here. So this radius we have dug a tube well. Inside again we have dug a tube well. So like that, at small radiuses again we have dug, but here we are asked to find what is R. So let's go back here, and let's use some information which we have been given. So we know that the rate of pumping is there. We also know these distances. So since you've already watched the lectures, can somebody tell me which formula, or which theorem formula we'll be using? Like, it's known by a specific name. Anybody? Okay, let's just go ahead. We'll be using the Thiems formula, where this formula goes that Q, which is the rate of pumping, that is how much we can pump from that particular well, the rate of pumping is equal to Km, which is the transmission coefficient. So this is it's a constant basically used. So it's a transmission constant of that aquifer. That is, for each aquifer means, you know, that the layer where that water is being stored. So so this is of that particular aquifer, the Km constant, into, we have H square divided by H square divided by log to the base 10 R by R. So this H is nothing but the overall depth, or the depth in which the well is. So if you go to this question, this overall depth is what is given, and that information is already given to us. So this is our H, and the other H's is basically this one, like whatever this is happening, like that is the small h. Like for each one, how do we calculate? When we take the numbers, that will be more clearer to you. And this R is what we've been asked to find in this particular question. So it's basically the radius of influence. Radius of influence, that is what we will be finding. And this R, the small r, is the radius of the test well. So as I said, you've got certain test wells also. So this is the radius of, so this will be the formula which we will be using for, yeah. So this will be the formula which we will be using for all the three coming questions. So let's start off with the formula. So we know that, let's just write down the information which is there. So radius of the well, let's just go back. What is the radius of the well, which is, yeah, so we've been given that it is 30 centimeter in diameter. So radius of the well is 15 centimeters, right? Or we'll just write everything in meters because our final answer we want it in meters. So it'll be 0.15 meters. Now we also know the rate of pumping. That is Q, which is given in the question to be, I'm just going back, 1500, yeah, 1500 liters per minute. That is Q. So 1500 liters per minute. Now, for test well 1, so we have two test wells. So test well 1, we know that the radius or the distance in which it is located, let's just go back and see how that is. For test well down, which is 30 meters away. So the radius is 30 meters away, and the depth, whatever we are talking about, our small h, which is 1.5 meters. That is what is given. And for the second one, it is 60 meters away and 0.6 meters in depth. So let's just go ahead and write both. So it is 30 meters, and our drawdown, which is happening, which is given, it is 1.5 meters. And for the other one, our radius, that is small r, is equal to 60 meters, and our drawdown is 0.6 meters. So by drawdown, you know, no, how much it is going down, like the water table, how much it's going down. So it is drawing down by about 1.5 meters in this case, and it is 0.6 meters in this case. That's what the term drawdown we're using over here. So we also know that the overall depth of the well. So the depth of the water before it was pumping, like before pumping, the overall depth, it is 40 meters. So the overall depth of the well, which is nothing but our capital H, is equal to 40 meters. So we have taken the information. So now let's try putting this in the formula. So Q is equal to, here I'm just writing it once more over here so that square divided by log 10 r square divided by, sorry, no square, r divided by r. Yeah, so km, I'm just leaving it like that because we do not know the value. Even q, I'm just leaving because we won't need it right now. And our first case we are taking, that is, so for 40 meter depth minus our, yeah. So here our h, this is drawdown. This is not h, that is, this is how much it's coming. H is whatever, like what is the water level, that is what H is. So whatever is remaining. So we know that this is 40 meters. So H will be 40 minus 1.5. Similarly here H will be 40 minus 0.6. So for the first case I'm taking, that is for the first tube well, our H will be 40 minus 1.5. Now we have to square it, divided by log to the base 10. Our R in this case is what we have to find. So leaving it as R, and the radius is 30 meters. So this is our equation 1. Now for the second case, that is second tube well, again 40 square minus, we have 40 minus 0.6 in this case, whole square, divided by log 10 r divided by 60. This is our second equation. Now both are equations for q. It's the same thing, equations for q. And we do not know r. So we have got two equations, and we have basically have only one unknown, which is r. Like these are common, so it'll get cancelled. So we are equating 1 and 2. And yeah, so let me just do this. I mean, we're just equating it, so we can just start solving it right away, or maybe we can do some simplifications here if required. That is, how much would this be? So this is 38.5, the whole square is what we will be taking, and in this case it will be 39.4, the whole square is what we will be taking over here. And because if we simplify and write, it will be much easier. So yeah, so I'm just equating it like that. So km into, you can do the whichever is convenient to you, like that way you can do the calculation. Like this is, like for me this is much more convenient, so I'm going ahead and doing this way. So it would be So this calculation, I'm going 40 square minus 39.4 the whole square. You can parallelly work it out and then check whether you're getting the same answer. So this what I'm equating, and for the second one, I'm equating km into 40 square, yeah, 40 square minus 39.4 squares, that is 47.64 log to the base 10 r by 60. Right, so, okay, so these will get cancelled. So basically we have these two. I'm just taking, just taking this here. One second. Yeah, you can do the calculations. I'll just add one more page here so that I can do the calculations. Yeah, so just equating them. Yeah, so log 10 r by 13 equating. I'm just rewriting it here so that the calculation is clear. R by 60. So now I'm just rearranging. So this is to, so I'll just rewrite whatever we got till now. I'm writing all the steps so that the calculations are also clear, because this is mainly a formula application, but where it goes wrong is in the calculation. So in some solving, things might go wrong. So I'm giving all the steps. If there's any doubt in any of the calculations, feel free to ask. You can put it in the chat box, or you can even unmute yourself and write. Sorry, unmute and ask. Yeah. So till here, I think, Emil, did you put the answer for this question? I'm afraid that's not the answer. Maybe you can just check your calculations once more. Okay, so yeah, you can just check it once more. Like it's a bit different. Okay, has anybody got the answer? I'm just not writing the final answer. I think if till here the calculations are clear.
95.9 meter.
Yeah, right. Perfect. It is 95.9. So we can approximate it as 96 meters. I'm just waiting for a confirmation from everybody else so that it's clear. Or if you're still doing the calculation, you can just say that. I can wait for a few more minutes. All right, so I think it's clear. So basically, so what does this signify? It basically signifies that our radius of influence, it is for about 96-meter radius, there is an influence which is happening. So when we are constructing another well or something at a radius of 96 meters, then we need to be careful or on the decreasing or the reducing water level. So it's ideal to construct a well beyond this region. So there's an influence which is happening over here. Right. So let's go ahead. Now the next question is, what is the transmission constant? So this is basically Km, which we were talking about in the previous question. So this is a very direct formula application because we've already found that our radius of influence we already know. So we have Q is equal to Km into, I'm just writing it again, h square minus log 10 R by R. So we already know this is 1500 and km is what we are supposed to find. Now we have 40 square minus, if we can take any case. So here I'm taking the first case which is given. So 38.5 the whole square divided by log of. So here instead of r, I'm writing 96 itself because we have already got that answer divided by 30. Right. So this is now km is equal to right. So it's around 0.64, which is this one, option C. So I just went a bit fast in this calculation because it's just direct formula application. You may take a screenshot of this and keep, or the videos will obviously be available to you. We'll proceed to the next question because we have a few more questions to discuss. And with respect to the same question, now we've been asked to find the maximum discharge of the well. So what do we mean by maximum discharge? So how much of water, like or with the speed, like how much volume of water we can get out. So this is actually a very theoretical value. Like we will never get this maximum discharge out of the well. So what we do is we know that at the point, like at the deepest point from where the water is rushing in, that is if we have the well here, the deepest point, that is where our maximum discharge will be. So if this was our H, like the overall H, we were talking about depression which is happening, which was the depression head, and we were this height we were talking about H minus H and all that. So over here we are talking about maximum discharge which is happening. So where are that H or whatever value we are talking about becomes zero, so that we get the maximum discharge which is happening over here. So basically we are taking H equal to 0. So let's go ahead and do this. So Q is equal to Km into H square minus H square. So we're interested in finding Q. So this is again direct application. So 6.4 is previous question we got this. We're applying it here. Minus, so H over here, H is 0. So 0 square minus log 10 96 divided by, we already, so yeah, so this R is basically the radius of this well, right? Because this is what we are talking about. And we already found that the radius of our well is 0.15 meters. So here we'll put 0.15 because here we are talking about that particular well only. Yeah, so this calculation also. This is the answer that we are getting. But the options are in meter cube per minute. So we'll just convert it into yeah, the option is in meter cube per minute. So we can just uh, convert it. It's just a decimal, like changing the decimal point. So we'll approximate it as to which corresponds to our option C. Right. Right. Very good, Emil. Yeah. So your answer is there. I just saw it. Yeah. So we can, if there's any doubt in this set of questions, like 2, 3, and 4, you can ask now. Okay. Very good. Let's proceed to the fifth one. Okay. So the previous questions which we discussed in the lecture also we have discussed. So whatever we're going to discuss right now, it's not in the lecture. The solution or the problem is not there, but we have learned about this theory. So this is a bit additional. So it would be useful for your final exam also. So the question is, we get a plastic tank with a volume of 1 meter cube and we fill it up with sand. We start adding water to the tank and the voids within the sand start to fill up with water. We continue adding water until the water reaches the top of the tank, so it's not overflowing. In total, we are adding 330 liters of water. What is the porosity of that specific sand? So in this question, we've been asked to find what is the porosity of sand. So we have already learned in theory what porosity means. So porosity basically means how much of void is there. So if we have, like, if this is the composition, then this volume of void, like how much void is there in a particular substance, is what is known as porosity. So the formula, we have also learned the formula for, like, how do we find porosity, as the volume of void which is there in that divided by the total volume. So this is the formula, like how we would be finding. So let's see whether we can find the information of how much volume of void is there. Like, let's see whether we can get the information from the question. So we know that the overall volume is 1 meter cube. So the total volume, we already know it is 1 meter cube. And we are filling the entire volume with sand. So that is sorted. And into the sand, we are adding around 330 liters of water. So we see the unit is different. So in the previous question itself, we did that. So we have like 1000 liters is equal to 1 meter cube. So we need to convert this. So if we have 330 liters of water, that is 0.33 meter cube of water. So we will be putting it as 0.33 meter cube. So yeah. So that's the answer, 0.33. So 33% of porosity is there, which is option D. Yeah, very good. Asmita and Emil, you've already got it. Oh, awesome. So I'm assuming there are no doubts. Let's proceed further. So this question talks about uh, design an open well in fine sand to give a discharge of 3 liters per second when worked under a depression head of 2.5 meters. Assume the specific heat yield for sand is 0.5 cubic meter per hour per meter cube. So the specific yield is given, right? So what do we mean by design an open well? Like, okay, firstly, what do we mean by an open well? Can somebody respond? It's there in our lectures. So anybody, Asmita, Devsena? Okay, so it's nothing like open well is basically the normal well that we have. Like, we have one side open and we draw water from that. That's the open well. There are certain like closed wells also where we have like both the sides locked and we'll be drawing water from using pipes and all that. So this is basically an open well is a normal well from which we draw water. And so whatever we discussed before in the previous question also of rate of pumping, that also corresponds to our open well. So here we've been asked to design an open well. So by design, it's not too complicated. It just means find the radius. That is, how much of radius should we design the well so that we get a good discharge. So here we are talking about the yield or the specific yield which is happening to that well. We discussed about Darcy's law in the lecture, which talks about uh, based on the difference or the potential difference which is there, the yield happens. Darcy's law. So there are certain laws like that. So here we will be using one of the empirical equations which we have already learned. So we learned that our yield is equal to C dash by A, which is our specific yield. So this whole term corresponds to the specific yield which is there into the area A, which is the area, into S, which is the depression head. Right. So again, this comes from the recuperation test, which happens. So the recuperation test means that if you have a normal well, and if we like if the water level is this much, we draw water and the water level reduces. So imagine it comes down to this much. Then after some time, that is after a specific duration, when we are talking about what to what height, like after a duration, like imagine after 1 hour we are checking, so then the height of this well will increase. So to what height is that increasing? So we take those information, and that's how we come up to all these. So if you I mean this formula, the derivation and all these details are there in the lecture. So if you have not seen that yet, I would advise you to look that, so that the whole idea is again clear. Here we'll try to solve problems with this. So we have been asked to find uh, the diameter, like what is the diameter. So let's just write down the information which is there. So Q we already know, which is 3 liters per second. I'm just converting it as 0.03 meter cube per second, and like we need it in hours. So let's just go ahead into 3600. So that comes up to 10.8 meter cube per hour. So this is what is there. Now specific yield also, it is given in the question. Assume the specific yield for sand is given to be zero point 0.5 cubic meters. So yeah, so cubic meter per hour. So that is what we have. Depression head, S is also given. S is equal to 2.5 meters. So it's a direct application. So let's just put in 10.8 is equal to 10.8 is Q, if you remember. Like, yeah, that was a Q. 0.5 into A into 2.5. So A is equal to 10.8. Yeah, so let's just do the calculation. Yeah, so this is A, which is our area. Now we've been asked to find the radius. So just going ahead. Yeah, the answer. Asmita says 7.3. Was it for this question? 49. Maybe you can just check once more. Okay, yeah, I think 3. Yeah, ML has got it right. It is 3.3. Asmita, maybe you can just check your calculations, because this one, when you do like divided by 3.14, if you're doing this calculation, it comes up to 3.32. So we'll approximate it as 3.3, which if we go back is yeah, 3.3, 3.4. So this one comes to the closest answer that we can get. So it is option C is the answer for this. Asmita, is there any doubt? Okay. Okay, perfect. Yeah, thanks for your response. If that's the case, then we can move on to the next one. So yeah, so in this one, this is also pertaining our recuperation test. So it's
Madam,
meant.
we can't see the question. We are seeing your blank page.
Oh,
Now,
sorry,
now
it
it is
didn't
okay.
load.
Now
Yeah.
it is okay. Now it is okay.
Okay, perfect. Yeah. So these would be the last two questions which we will be discussing for today. So during a recuperation test, the water in an open well was depressed by pumping by 2.5 meters and it recuperated 1.8 meters in 80 minutes. So this is what we were talking about before. That is, if you have well, so this one is mainly talking about that test. How do you find the specific yield from the recuperation test? So the water level which was there, so it reduced initially, it reduced by 2.5 meters and then it again came up by 1.8 meters. And what is the duration by which this happened? In 80 minutes it happened. So this duration is also given. Now in the first question we've been asked to find the yield from the well. So again, if I go back to the same same formula, into a into the depression head, like this is it. So this is the specific yield which in the previous question was given, but here we have to find this, like we are interested in finding this also, like c dash by a is what we'll have to find first in order to solve this. And let's just start that way and then go. So from the recuperation test formula. So initially this formula which we use basically is a derivation from our Darcy's law, that is based on the potential difference which is happening. Now we are again going on to that recuperation test or whatever formula was derived based on that. So we have C dash by A is equal to 2.3 divided by T log of S1 by S2. This is the formula. So this is this. And now T is this duration which we are talking about, that is in how much time it is getting recuperated. And S1 is basically our depression head just after pumping. That is this 2.5. Like after pumping, what is the depression head which was there? So it's the depression head just after pumping. And our S2 is the depression head after this time duration T. That is depression head after, this is capital T we used here, yeah, after T time when the pumping is stopped. When pumping is stopped, right? So so here it is not 1.8, but we'll have to take the difference. That is, it's coming up, right? So we want to find the depression head, that what is the difference which is there. So this will basically be our difference. That is, it came down by 2.5 and it went up. So our depression head in this case would be 2.5 minus 1.8, which is 0.7. That is our S2. So that will be our, I'll just use a different color so that it's clear. So just going back. So this is our S1. This is our S2. And duration, again, yeah, we have already marked that. It is 80. Rest all we have. So I'm just writing it down here. Q is equal to 2. So 2.3 divided by this one, it's given in 80 minutes. But we have to convert this into hours, because in formula, it said that it is the duration in hours. Like the formula says that duration in hours. So that is one catch over here, which you'll have to convert. So 80 minutes, we'll have to convert that. So that comes up to 80 by 60, which will be 1.33 hours. So let's put that here. So it's 2.3 divided by 1.33 into, just putting, so log of 2.5 it is, divided by zero point 0.7. So this is our specific yield which we are finding. So now going back, we'll be having our Q is equal to our C dash by A, which is this, into, now we need to have the area and the depression head. So I'm just putting that, instead of writing this, I'm directly, let's just go, directly putting the area and depression head. So area, uh, we already found that, right? So we can just put it from this one. Okay, I think you can proceed with the calculations because you can proceed and then you can check whether the calculations are right. So this D, which we already found in the previous question, I'm just going back. Yeah, so this was 3.3. This is 3.3. This thing alone comes up to 9. Yeah, very good. Very good. You've already got the answer. It's converting into liters per second. It is, yeah, it approximately, like I got 36, so liters per second. So it comes up to 10 liters per second. Yeah, 9.46. You're approximately near, because then we can look into the answer question. So the nearest answer what Emil got, and my calculation was in a different method. So 10 liters per second is the answer. Any doubt in this particular question in calculations or in theory, anything? No. Okay. So we can proceed on to our last question. So that also corresponds to this, the same thing, like what has happened. So here we found the yield, which was Q. So let's see what the next question asks. So the next question is asking, what should the diameter of the well be if the yield is to be 8 liters under a depression head of 2 meters? So this is kind of similar to our question number 6, which we did, where we had to design a well. So that it's somewhat similar to that what's been asked. So let's go ahead and let's see. So here we've been asked to find the diameter. So I'm just writing. So we'll go ahead with the same formula, into A into S, right? So here we know the yield which is given, which is 8 liters per second, and we will convert, because we were taking our duration in hours, so we will convert this into hours, and then like liters per second into liters per hour. So it just goes like 8 into 3,000. 600 divided by 1000, I mean meter cube per hour, that is what we're taking over here. Uh, meter cube per hour. And this we already calculated. I'm just going back. We already know this value, 0.955. So I'm not doing the calculations again. Previous question, we just found it. And area again. So I'm just leaving it as d square so that we can come back and do the calculation. So now here s is given to be 2, like it, not like in the previous question, it's given to be 2. So that also we'll have to plug in differently. So yeah, so now just going ahead. I'm just leaving this as such because it anyway comes into the root. So we'll have to do it at that time. So just simplifying it. Yeah, I'll just write the rest here. Right. Very good, Emil. You got this also right. Yeah, this is amazing. 4.4. Anybody, any doubts on this particular question? Let's just see whether that's there. So yeah, it is there in our options. So it's option B, 4.4 meters. Great. So that's all I was intending to discuss today. These numericals on finding the yield, designing of a well, surface runoff. So we discussed all this. For your assignment, for the upcoming assignment for this week, I think only the first two questions would, so that sort of questions are there. The other questions, but again, it's important because for exam, it can be there. So if you have any doubts in this week's or next week's, I think the previous week's solutions have already been given. So if you have any doubts, you can ask now, or you can even put it up in the discussion forum, and I can take it up in next week's lecture also. Like anything is fine. I'll just wait for a couple of minutes if you have any doubts. If you don't have, you can leave. See you all next week if you don't have any doubt. If there's any doubt, you can stay and you can ask. Thank you, Asmita. It's nice to see you around. Like it's good. Like some constant. Even Devasena, I remember you were there last time. Even ML was there last time. It's good. Your interaction makes it much more enjoyable. Like when you're solving it together, it is really good. Great. So we'll see you all next week, and all the best for submitting this assignment. It's uh, it's really good. Yeah. Bye bye. Have a good night and enjoy your evening.